All right, what you see here is a script that is actually doing two things for us. One is it's helping us to actually test this model, but also I use it to create new data. So what I pass here into action is what I'm going to be thinking the entire time the environment is running. And then all we're using action for is down here where we figure out did we get it right or wrong, as well as when we go to actually save the data, the FFT data that was used to make that prediction, so we can continue training models. So we're just always building the data set bigger and bigger. So with that, let's go ahead and try thinking left, and let's see how we do. 8. Okay, decent. Basically what I get here is this is how much data I have, just so I kind of know where I'm at. Obviously, that box is what's able to move, so I'm thinking left. The hope is that that box continues to move left. There's 3 action choices, left, right, or none. We can see here that basically left was the predicted action 52% of the time. I do actually collect more information. I just haven't started printing it out yet. But what happened there was probably mostly like none gets predicted a lot. So obviously predicting none is much better than predicting right, at least. And as you can see, we did move beyond that middle thing. So that was okay. Let's go ahead and try right. That worked pretty well as well. Cool. Welcome everybody to the second BCI video. The first video, the engagement, excitement, the passion was off the charts. I even had people pouring over into email just to tell me how excited they were for the series, which is really cool to see. I'm glad you guys are interested in either learning about this or just seeing me fumble about here. All right, on to fixes and findings from the recording of video 1 till now. The first major issue was the bursting that I was experiencing, and possibly bursting is still the wrong word, but nobody corrected me on that, so I'm going to keep calling it bursting. My solution was first I tested on my MacBook with the Python or OpenBCI, and I didn't have that issue, and then I tested on Ubuntu on my main machine because I dual boot Linux. And I didn't have the problem. So my solution was actually just to change operating system. Now that might be a little unruly for everybody. So William Croft linked to this document here, which apparently is under deprecated documents, but I'm assured it still works. I haven't tested it, but they say it works. So if you're on Windows and you need to fix that issue, check that out. Next, just to solidify the actual sampling rate, the Cyton board alone, which is 8 channels, will give us 250 hertz sampling rate, and then the Cyton plus the Daisy board, so the board just sits like on top, gets us to 16 channels, which is what I'm using. That is 125 hertz, and this is a limitation of the Bluetooth. This could be fixed with the Wi-Fi board, which I actually do have. I'm just not going to use it yet. I'm told I see the best word is experimental. So it can be kind of a finicky board to use. So I'm going to hold off on that until I've done some other R&D. But yeah, it definitely exists. And finally, the Nyquist theorem. So I was actually having a disagreement with Daniel, who I work with, about how many samples would you need raw to reliably sample to some lesser value. Do you need 2 times? Do you need 4 times? What would you actually need? And we're going back and forth arguing, philosophically on the matter. And then I just decided to Google it. And sure enough, I found like a Quora post, which then linked to this, which it, providing all the proof and stuff that I can't validate, but I'll assume it's correct. Basically, the crux is greater than 2. So if you want 60 hertz, you need a raw sampling that is more than 120 hertz. So that makes sense because also on the OpenBCI GUI, if you're, like I'm using 125 hertz, it goes to 60. Okay, So I'll take that as expert validation. So moving on, now that we know those things, what is our objective, right? Our objective is, at least to start, I want to move something on the screen. And as you've already seen, I'm starting to get there, but how do we do it? So we need something, and I want to use deep learning. So we need something to pass through this neural network model that is like useful information. So I did start with OpenBCI, and I was doing my own signal processing with SciPy. This is fairly complex. It's not that hard, but you need to account for any fluctuations in the actual sampling rate. Like ideally it's 125, but sometimes that's coming faster or slower. So it's hard to account for that. And I just don't know, like, do I need to account for that? Or is that fluctuation so minimal that it just doesn't matter? So I don't know. I don't have the answer to that. So instead what I wanted was actually something made by someone who's an expert on the matter, right? And my assumption is that this right here, this FFT plot, would contain useful information for the machine to determine left, right, or plausibly none. Initially, I was thinking just left, right, but then the question was, we're probably getting a lot of noise here, so maybe introducing a third action, none, would help the neural network to determine what's truly left, what's truly right, and so on. So anyway, regardless, mostly it's just move left, right. Is that information present inside of here? I hope so, right? That is my premise. So I need this, right here, and I could do it, and like there's lots of sample code online to do it. There's two major issues. One is just like speed. You need to be doing it at a pretty high rate. So that's one thing. And two, the same thing as before, I can't really validate code that I don't know how to validate it, right? So that's a problem moving forward. So really what I want is this. I just want this graph, right? So anyway, I was discussing with the people at OpenBCI over email, and they've been super helpful. One of the things that they linked me to is this Jupyter notebook that uses the OpenBCI and then also combines p.2 graph. And I've actually never personally used p.2 graph, but it's really cool. So this is actually a really cool example of p.2 graph, if nothing else. And this is what it should look like. So it's almost like a replacement of the OpenBCI GUI, especially if we did band power down here, right? So in theory, it's just kind of OpenBCI GUI in Python, which is just cool. It was just cool to check it out. But also I was like, oh, this will have the FFT code, and I can just use that, right? So I was like, okay, great. So so I did try it, and actually let me keep this up. One of the issues I faced was when I ran that, this is what I got. And obviously there's a couple of major issues here. So first of all, with EEG data, you want to do two things. You want to filter out things that are outside of the ranges that you're expecting to actually receive. So you use like a bandpass filter. Sorry if I butchered that. There's probably people cringing right now. And then also you want a notch filter. And the notch filter is to filter out the 60 hertz noise. So all the electrical equipment is just screaming out 60 hertz noise. So you just get rid of it because it's useless. So yeah, as you can see here, they've notched that away. But for whatever reason, this was mine, and it looks like I don't have, like, the 60 hertz noise got filtered out, but it looks like I've got, I don't know, 63 hertz, like a huge 63 hertz noise, and that was always there. It's not like that was like a one-time fluke. Also, the channel data just looks wrong. So I don't know what to think about that, but yet again, the recurring theme is I don't know how to fix it, right? Because I don't know what I'm looking at when I'm looking at this code, and it's going to probably take me months to like learn all the things I need to learn. Maybe not months, weeks, but a while to figure out, okay, here's where something's going wrong, and hopefully I'm assuming it's nothing wrong with the headset. So so there was that. But then I was linked to the actual GUI, which has a section which was up initially called networking, which allows you to take anything you want from here and pass it to Python over something called LSL, which I had never heard of. I think lab streaming layer. basically, if you use this, you can just set a constant stream over Python, which I'll show in a little bit. And then you just connect to it, right? And then you can choose what do you want to pass over that stream. And I was like, yeah, fast Fourier transform, let's do it. so that's what I wanted. But initially I threw 16 in here, and it just really wasn't clear to me. So like if I go over here, it just says like FFT can be now sent over LSL, which is cool. Then it sort of has some information here about for certain data types you want to change number chan to match the data type, but I wasn't really sure what that was talking about. So I threw 16 in here and I had a really hard time figuring out what was going wrong. But basically I was getting data that look like this, which doesn't look like this at all. But it's very clear there's like either wrapping going on here or it's multiple data sets, but I couldn't figure out what was going on there. But then eventually over email, yet again, I was given this, which I hope that I think this should be shared like on that page personally. But basically it just says you're going to get 125 floats, one for each bin per channel. And as I'm looking, it's like, oh, okay. So really what I want to throw in here is 125 for the channels. And once I did that, everything worked. So to show you an example of that, what was it? What would it be? Python 3.2. So I'll just run that one. Let's see. Oops, not Python 3. Python 3.7. So this is at least closer to what we're expecting. Now, obviously, this is just single frame. I'm probably moving my head, so we're seeing quite the fluctuation there. But anyway, yes, this is the data I was after. So now, finally, I've got that information. I can walk away from the subject that I am very weak. I don't know really anything about beyond. I've worked with Fourier transform data before, though, but it was for audio. But I can finally take this and do the DSP or digital signal processing that I do know about, which is passing that through a neural network and hopefully classifying right-left or right-left none and so on. So then the question is, okay, what kind of neural network are we going to use? Also, how do we make data and all that stuff? So now what I'm going to do is go over the actual code there. Okay, so this was kind of like the first code that I grabbed to get the LSL or LSL data to get the FFT or fast Fourier transform graph, which basically is this data here. So again, you just choose that type. You can name it and type it here, and then you say 125 channels because we're sampling at 125 hertz, and then you just hit start here. So once you've done that, you're done, right? You just leave this UI up, and it's just streaming that information, which is super useful because if you've ever had to work with like serial connections to things, it's kind of a pain in the butt, and very often you're just cycling power over and over and over. It's very hard to like iterate on the code. There's usually like clean ways to exit, but often you'll hit an error or something like that, and you just, it's a pain. So this is super cool because you don't have to deal with that. So right now, this is just streaming out this information, and then in the code, we just collect that information. So we're just saying, hey, give us the stream that's of type EEG. You could either do it that way, or you could grab it specifically by name, which is pretty cool. Like I said, I've never used PyLSL, and I'm guessing most of you probably haven't either. So cool, and then we can grab that specific stream. It'll be the only one in this case because we're not streaming anything else on the other channels, but you could stream the other things as well. So you connect to that, and then again, it's going to come in chunks of 125, and as we already saw in the docs, it's 125 data points per channel. We have 16 channels, so we're going to get 16 channels of 125 data points, and we're just going to keep cycling through that. So one thing I could do is rather than say 5, we could do this, I don't know, for 500, or we'll do 5,000. And then let me go ahead and open in terminal here. And we'll say Python 3.7 to stream FPS. So this is just the actual frames per second. So we're seeing we're getting about, I don't know, 22 22, 23, now it's 25. I did notice that it starts off kind of slow and then eventually we'll go to about 25. And then when it's done, we'll actually see the graph, hopefully, if it finishes anytime. And then here, I'm just plotting the data chan up to 60 hertz. So we actually have more information, right? So what we could say is, let's go back to 5 and just plot the whole thing. We actually have data all the way to 125 hertz. Possibly. Why? Actually not sure why that is angry at me. Why are you angry? Huh. I don't know why it got angry at me there. Anyway, so as you can see, it does actually go beyond that. But again, Nyquist theory. Anything beyond 60, I suppose, is probably useless. Like, we can't actually, it's not reliable information, so we toss it. So anyway, the information we actually want is at this point here. So now we can take this data and we can pass it through a neural network, but we have many questions. What kind of neural network do we want to use, right? And I know most people are going to think recurrent neural network, but if you've been watching any of my tutorials recently on machine learning, recurrent nets are so 2018. Really, convnets are also the king of sequential data. So we're probably, at least what I've started with is a one-dimensional convnet, and I'm actually not even using anything like attention. I'm not passing a sequence of information. I'm literally passing just this data right here, and that's it. And then we're just constantly making predictions at about 20-something-ish frames per second. So it just becomes kind of a combination of all of those predictions given, and that will create what ends up actually being moved. So so the first time I did it, basically it's just a bunch of code that, let's see, stream, blah, 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 environment. You already saw the environment, so I'm not really going to show that. And then this just this was the first time because I didn't have a model to move something around. Basically, I say, hey, here's the action I'm going to think about. And then we actually run the environment. We run through that environment, and then we save that data to whatever that action is. So now I've got this data directory, and we've got left, none, and right actions, and it's just full of NumPy arrays of just a bunch of FFTs of the thought right. So I've done that with left, none, and right, and like I said, right now I'm just passing it through a 1D convnet. Possibly later I'll do multiple samples per thing that I pass. So it could be a 1D convnet. It could be probably a 1D convnet with like attention or something like that. But right now I'm just trying to get a decent amount of information. I'll probably also try a recurrent net. Convnets are doing better. Also, convnets are way faster, so I can much more quickly iterate through things, test them, and run it live. Because what I ended up doing was after I train a model, I actually run this script here, which loads that model, and then, hey, I say, I'm going to think left. It's going to use that model to read that FFT data, make its prediction, and hopefully go left. And at the end, it saves the data under, whoops, not there, here. It'll save that data as a left, right, or whatever. So anyway, this is the script that I usually end up running the most, which is just simply constantly running models. And then it's almost like two things are happening at the same time. We're creating data, and I'm actually kind of testing the model at the exact same time. So there's that. And then also I'm just collecting a bunch of data in terms of accuracies, so later I can create confusion matrices and all that. So that's where I am right now. I just ran through a ton of things. I totally understand that was a lot of information. At some point I will release at least the training data. I just want a little bit more. I want to make sure I'm on the right track. I'm still like totally second guessing things and like not really sure if it's working, but at least so far, the left, right, and none, I am consistently better than random. It's about somewhere between So there's 3 options, right? So that means random is 33%. So if I'm thinking don't move, right? More, it's about 50%. Well, on none, it's like 60, 70, 80% accurate. Like if I'm not thinking left or right, it's very accurate. And I guess that's probably because nothing's going on. But if I think left or right, that's what's very difficult for the machine to differentiate. And again, there's a 33% chance to get that right. And I'm getting about mid-40s% accuracy. So I know there's something there, but as you could see in the beginning, there's a lot of like wiggling going on. And then there's plenty of times I'm thinking left as hard as possible, and that box goes right. So definitely lots of things to work through, more data to create, possibly changing up the model, whatever. And even if I go with a recurrent net, I still have the data that would be required for that. So really right now I'm just collecting FFT data on thoughts of actions. So from there I can go many ways, unless I end up deciding FFT is not informative enough, right? Garbage in, garbage out. So like I said though, I think it is purely because I've got an edge clearly already with a pretty basic one-dimensional convnet. Like right now, the convnet is, I think, 32 by 3, but I've been trying like a ton of different ones, but I can pull that up as well. Yeah, so right now we're doing a 32 by 3, and that's really it. And that seems to be actually working, which is really surprising. I didn't think I was going to be able to get results as quickly as I did, but once I got the FFT data, I was able to start training something at least. So, but that said, I think left and right should be pretty simple to detect just based on channels alone. So anyway, we'll see. Lots more to go. If you've got questions, comments, suggestions, whatever, feel free to leave those below. Also, shout out to another batch of new channel members: Eduardo Monino Esteban, Benjamin Bianchi, Dergema, Mark Abisu, Joao Pedro Vasconcelos Texiera, and James Seifert. Thank you guys very much for your support. You guys are awesome. That's it. I'll see you guys in another video.